Hi guys, welcome back to the channel, and in this video we will be deriving the big four kinematic equations. So let's start off with the first equation. We have delta x is equals to v minus v naught divided by 2 times t. So before we actually derive these four equations, we have to know this basic principle. We have to know that velocity is the derivative of distance. So distance, which is represented by x. When we take the derivative with respect to time, we will get velocity. And if we take velocity, which is represented by v, take the derivative of this, we will get acceleration. And this is the derivative of velocity with respect to time as well. And we will get acceleration. So if you want to go back, you simply have to integrate. Okay? So for the first one, we have velocity, distance, and time. So we have to start with this principle here. So we know that velocity is actually the derivative of distance, which is represented by dx over dt. So if I want to integrate this, I have to first transpose this to the other side so we can integrate both sides. So we will have v dt is equals to dx. So integrating this, and then for this part, it is bound from 0 to t, because when we are calculating time, we always have to start from 0, because time is never negative. And then for x, since we don't have any idea what the distance is, we can start from x1 and then to x2. So this one, the v here is constant. So it's just v times t bound from 0 to t. And then this one is simply x bound from x1 to x2. So this one will be equal to v t minus 0, and that is equals to x2 minus x1. And simplifying this further, we have vt is equals to the change in distance. This is simply the change in distance. And we know that anything multiplied by 0 is 0. Hence this equation. And we have to know that the velocity here is actually the average velocity. And how do we calculate the average velocity? We take the final velocity minus the initial velocity divided by 2. So it's v minus v naught divided by 2. So replacing this here, we will get v minus v naught divided by 2 multiplied by t is equals to the change in distance. And that is our first equation in the list earlier. Okay, so taking the second equation, we have acceleration and velocity, right? So what we're going to use here is this principle here. We know that acceleration is actually equals to the derivative of velocity over time with respect to time. So what I'm going to do here is simply the same thing. So we will transpose dt first to the other side. So it'll be a dt, and that is equals to dv. So integrating both sides, this one with respect to time. So that is from 0 to t. And then with the velocity, so that is from the initial velocity represented by v naught. And then the final one, which is v. Okay, so it'll simply be a t minus 0, and that is equals to v minus v naught. So this one will get canceled off. Again, anything multiplied by 0 is 0. So we have at is equals to v minus v naught. So if you want to make the final velocity the subject of the equation, simply have to transpose this to the other side. Okay, so v is equals to v naught plus at. And that is our second equation in the big four kinematic equations. So we have checked this off the list and this one as well. So let's deal with number 3. So in here, we are also going to use this equation here, but we have to start with this principle. Why? Because there is the change in distance here in this equation as well. So we have to start from there. So we know that, again, velocity is equals to dx over dt. And we know we have derived that the final velocity is actually equal to v naught plus at. So we just have to replace v with this part of the equation. So we have v naught plus at is equals to dx over dt. And we're just simply going to do the same thing. We have to first transpose dt to the other side, and then we integrate. So we will have v naught plus at dt is equals to dx. So if you want to integrate this one with respect to time, and this one with respect to the distance, this one is bound from 0 to t again, and then this one is bound from x1 to x2 again. And then we have to distribute dt to the variables inside the parentheses. So we will have the integral of VO dt bound from 0 to t plus the integral of at bound from 0 to t dt, and that is equal to the integral of dx bound from x1 to x2. And this will simply become VO t minus 0 plus the integral of t is actually t squared over 2. So it'll be a t squared over 2 bound from 0 to t. And that is equal to x2 minus x1. So how do we simplify this definite integral here? We will have VO, because this one is canceled off. VOT plus 1/2 a t squared minus 1/2 a 0 squared. And that is equals to the change in distance. And since this is multiplied by 0, again, this will simply be equal to 0. So simplifying this equation, we will get VOT plus 1/2 a t squared is equals to the change in distance. And this is the third equation in the big four equations that we listed. Okay, so this one is checked off the list as well. So we have the final equation, which is v squared is equals to v naught squared plus 2a delta x. So how are we going to do that? As you can see here, all of the elements in this equation, which is the velocity, the acceleration, and the distance, are all involved in this equation. So let's start with this one. Okay, let's start with this. We know that acceleration is actually the derivative of velocity over the change in time. But how are we going to incorporate distance here? So what I'm going to do is I'm going to express velocity in terms of its differential form as well. So that is dx over dt. And since there's dt here and there's a dt here, I can make this the subject of the equation, and then I'll replace it in the first equation that we started off with. So we will get dt is equal to dx over v. And then this one, I'm gonna replace it in this equation. So we have a is equals to dv over dx over v. And since this is in the denominator of the denominator, this will go into the numerator. So we will get a, and then this one, I'm going to transpose it here. So it's a dx, and that is equals to v dv. So integrating this, we will have a, and then x bound from x1 to x2. So this is bound from x1 to x2. And then that is equals to this one, the integral of v dv is actually v squared over 2. And then this is bound from v1, v naught, and then the final velocity v. So that is bound from v naught to v. So simplifying this, we have a delta x is equals to v squared over 2 minus v naught squared over 2. And simplifying this, we can transpose 2 to the other side. We will have 2a delta x is equal to v squared minus v naught squared. And if we want to make v the subject of the equation, we will get v squared, and that is equal to v naught squared plus 2a delta x. And that is our final equation in this list. So now we have derived the four equations, and that is how you simply can remember it without having to memorize them all. So I hope you guys learned a lot from today's video. Thank you for listening and stay tuned for the next one. Bye-bye.